Hello, this is Eric from UNC Charlotte, and today we'll be talking about parallel computing. Parallel computing is a set of techniques to accelerate the execution of a program by using multiple processing units simultaneously. Today, we will see why almost all modern computing systems contain multiple processing units. We will also see the different forms that parallel computing can take on modern systems. You may already be familiar with a related concept called concurrency. There is concurrency in a system when multiple processes are running at the same time and are working together to achieve a common goal. Typically, the primary concern in a concurrent system is to ensure that all possible executions of the system are correct, in the sense that the execution achieves the property that it is trying to achieve. While you may have programmed concurrent computing systems before, possibly with threads, concurrency can be found in many common human activities. Think, for instance, of the US postal system. Multiple customers drop their mail in designated collection box or give them to a postal worker. The mail gets aggregated in bins and brought to one of many sorting stations in the country. The mail then gets routed to the appropriate post office, where it is placed in postal delivery trucks. Finally, mail carriers will drive around town to place the mail in the appropriate mailboxes. The US postal system is fundamentally a concurrent system with many actors working together to achieve mail delivery. If the different actors do not work together, concurrency problems can arise in the sense that mail can get lost. While in a concurrent system, the primary concern is correctness, a parallel system employs multiple processing units to shorten the time it takes to perform a task. The concerns in a parallel system is to identify which computations can be done in parallel. That is to say, which computations can be done at the same time by different processors. Then, these computations are organized and given to different processors at appropriate times to accelerate the execution of a task. Obviously, parallel systems are concurrent systems, but the goal of a parallel system is not only to be correct, but also to be fast. Think, for instance, of asking a team to build a house. There are certainly concurrency issues in the sense that one has to lay a concrete slab before being able to build the frame of the house, or that one has to install insulation before putting up a drywall. But some tasks are more important than others if the goal is to build a house quickly. Delaying setting up insulation will prevent drywall from being installed, which makes it a more urgent task than painting the outside of the house, which can be done at any time. There are multiple reasons why parallel computing has become the norm in computing systems. One of them is Dennard scaling. In 1974, Dennard remarked that as transistors get smaller, their power density stays constant. In other words, as transistor shrinks, they use less power. The gain in power consumption from transistors shrinking can then be used to increase the frequency at which CPUs operate. Dennard scaling is one of the primary reasons why through the 80s and 90s, CPUs were getting twice faster every 18 months. An emphasis in the tech industry at the time was to increase programmer productivity rather than the performance of applications. Unfortunately, Dennard scaling ended around 2005, and we could no longer increase CPU frequencies without also increasing their power consumption. Though, can we just keep increasing CPU frequencies without benefiting from Dennard scaling? In short, not really. At the moment, the power consumption of a CPU is linear in the square of the voltage and linear in the frequency of the processor. Though, to be able to increase frequency, one usually also has to raise the voltage. In practice, the power consumption of a CPU grows with about the square or the cube of its frequency. What it means is that practically, doubling the frequency of a CPU costs as much power as operating 4 CPUs. So arbitrarily increasing CPU frequencies is not economical. And the industry started to increase the number of CPUs in the systems or the number of cores in the CPUs. Looking at historical trends, there used to be only a single core in CPUs until about 2005. The increase in CPU frequency and single-threaded performance started to slow around 2005. The capping of CPU frequency, coupled with the introduction of more cores, enabled to increase the processing capability of CPU while keeping the power consumption in check. This is why we see nowadays CPUs with dozens of cores. Even CPUs in laptops have more than 2 cores. The CPU in your cell phone most likely has more than 4 cores. Virtually all CPUs used in modern computing are multi-core CPUs. There are still some single-core systems out there, but they're usually for specialty applications. Another reason why parallel computing has become inevitable is that many modern problems are just too big to be computed on a single machine. There are technological limits to the amount of memory a single machine can have. Laptops rarely have more than 8 GB of main memory, and desktops rarely have more than 64 GB of main memory. A single server node usually does not have more than 4 TB of memory. So what options are there to process a problem that requires more memory than a single machine has? One could simply not compute the problem at all, but that's often unacceptable. One could program better to reduce the memory usage of the application, but that's often not feasible. One could use external memory, for instance by swapping to a hard drive, but that is usually very slow. Or one could leverage parallel computing and use multiple machines in order to solve your problem. Also, the usefulness of a computation may decrease if it cannot be performed quickly. The quicker a vaccine for COVID-19 could be developed, the more lives could be saved. If one wants to forecast the weather of tomorrow, the information is only useful if the computation can be finished before tomorrow. In a video game, one needs to render a frame within 16 milliseconds to be able to sustain 60 frames per second. Parallel computing is a practical tool to reduce the time it takes to perform a computation. There are 5 main forms of parallelism in modern computing systems. All the calculations performed at the circuit level are parallel. For instance, while executing a binary OR, the bits of the 2 operands are compared simultaneously. Also, modern SIMD instructions can perform up to 16 additions simultaneously. Also, modern CPUs are superscalar, in that a single core can typically execute more than 1 instruction at a time. Modern Intel cores can execute up to 6 instructions in a single cycle. Shared memory parallelism is the form of parallelism you are probably the most familiar with. It consists in using different cores to execute a single program within a shared memory space. Shared memory machines are typically programmed using threads, and concurrency issues are the most common problems. Distributed memory parallelism consists in using multiple nodes, each of which having its own memory space. The problem in distributed memory programming is often to reduce the amount of communication between the nodes. This is the form of parallelism that is usually leveraged for big data processing, and the form of parallelism that is usually associated with cluster computing and cloud computing. Most modern systems are equipped with accelerators, such as GPUs and FPGAs. These accelerators are typically built to improve the performance of a particular workload. GPUs, for instance, are particularly suited to improve the performance of geometric operations and most linear algebra kernels. While accelerators are usually parallel machines themselves, the most performance is usually obtained by intelligently distributing the calculation between the CPU and the accelerator. While circuit-level parallelism and instruction-level parallelism are forms of parallel computing, they are usually left for the processor architect and the compiler designer to take care of. Shared memory, distributed memory, and accelerators are the typical forms of parallelism leveraged by developers. Today, we have differentiated concurrency from parallelism. We saw that the end of Dennard scaling caused the design of modern multi-core systems, and that some problems are just too large to be processed on a single machine. Where there are 5 common forms of parallelism, programmers usually design parallel applications by working with shared memory systems, distributed memory systems, and accelerators.